squared minus c squared minus a squared over negative 2ac. When I plug in some numbers, this is 20 feet squared minus 37 feet squared minus 20 feet squared all over negative 2 times 20 feet times 37 feet. And when I do this out, typically when I do something with this, I know y'all have programs with calculators, but I will actually do it step by step, and I would write out the result of all this algebra and say cosine negative 1 is equal to just this number right here. That way, y'all's calculator doesn't trip you up. So that happens a fair amount, where you think your calculator is actually doing the calculation and you're telling it the wrong thing. Yes, please.
So on the test, we're not allowed to use our nice fancy calculators. We're just got to use the boring kind.
Right.
Are they going to have to also be able to do trig functions?
Oh yeah, of course. Yeah. And I'm not laughing at you. I'm laughing at you. I understand that concern. I would be concerned too. Absolutely, yeah. Trig functions, all your exponents and everything like that. So I'm not talking about a 50 cents calculator. I'm talking about a $5 calculator.
Gotcha.
Okay. So anyway, when we get this angle here, this is 22.3 degrees. Okay. So I've got a magnitude, I've got an angle. Am I finished? No. What else do I need? I need to find a direction. I also haven't finished this step right here. My alpha is equal to 22.3 degrees plus 45 degrees, and this is equal to 67.3 degrees. And somebody mentioned that, yes, I need to define what I'm measuring 67.3 degrees from in order for this number to actually make sense. So my angle C here, or my vector C here is just 37 feet, and then comma, 67.3 degrees north of the east direction. And that's a full answer for this problem. So if we look at our resultant vector that we've drawn out here, and we said that this angle alpha is the angle that we're interested in, we can see that this angle alpha is basically north of east. And so that's the kind of reference we use here. Let's see. So here's one example. Questions, comments, anything, please, John?
Do you always go north to east direction, or could you change
No.
the degrees and go east to the north direction?
Yeah, you can change the degrees to go east and north. I mean, that's all kinds of correct answers. Although we try to push to make it as simple as possible. And then also mastering physics it may have you specifically say you've got to say north of east or whatever, or the problem statement in the textbook maybe as well. But anyway, no, there's not just one correct way that we could report our findings. So in this case, we've just added 2 legs. We can certainly have the case where somebody makes more than just 2 stops. So in the case that we have multiple legs, for multiple legs, again, our total displacement is just equal to the vector sum of our individual legs. So if we have somebody that starts out of this position and moves over here, and moves over here, and say moves over here, our resultant vector again would just be the initial position to the final position. So if we assign these as D1, D2, D3, and this is right here is D net. Of course, we can write this out algebraically, or we can write this out. It's D net is just equal, of course, to D1 plus D2 plus D3. Okay, so let's see how we're doing. So, question for you guys. Which figure shows A1 plus A2 plus A3? So in this particular case, we've got vectors A1, A2, and A3 all have their tails placed on that one point. But what do we get when we add all three of those together? And think about our rules for vector addition, for graphical vector addition, the steps we go through. One or two, but that's okay. That's all right. That's fine. So what we see here is that our answer is C, and we've got a mixture of B and C, which I can understand why. Let me draw this out on the board real quick. So we've got vector A1, vector A2, and vector A3. We want to find A1 plus A2 plus A3. A1 starts off in this direction right here. So I draw my vector A1, and then to add A2 to it, I just draw the tail of A2 at the tip of A1, something like this. And then to add A3 to that, I just draw, I put the tail of vector A3 at the tip of vector A2, end up with something like this. And so my net result here is just right here, A net. Okay? And I understand some of the confusion here, or some of the problem here may have been just, well, I know how to do this, but it looks like it would be this to me, actually. Go ahead.
Oh, I was just going to ask, like, if you did move A2 to just, like, top of A3 and A1, and
Yeah.
just made it, like, B, would it be wrong, or would it still be the same way?
Can you repeat it one more time? I just want to make sure I got it.
Yeah, like, A2, you just move it on top of A1, so it's just, like, straight like that, and then make, like, B.
Okay.
Wrong, or would it?
Is that, so this parallelogram that we've got up here, forget that thing. Look at what I've done on the board instead. I think, actually, I may not be understanding what you're saying, because I think that you actually said exactly what I did up here.
Well, no, but, like, keep A3 where it was.
Okay. Okay, keep A3 where it was.
Yeah, and then have A3 and A1 make some lines. And
Okay.
A2 just goes on top of A1, and then you just make a triangle.
Okay. So you're saying, are you saying something like leave A3 where it is, and move A1 back, like this?
Yeah, just move A2 on top of A3.
So just move this one over here,
Yeah.
and then your net result would actually be, well, your net result wouldn't make any sense because you would have a third line that's going from the tip of one arrow to the tip of another arrow, and we never do that.
Okay.
Yeah. What's that? Yeah, something like that. Were there any more questions on this? Yeah, please.
With all the examples you've drawn up, they've always been tip to back.
Yeah.
These have three backs touching, and if this is all displacement, then what's the actual motion?
Yeah. See, I certainly, that's a great question. I certainly understand where you're going at, and we're not talking about displacement in this case. We're just strictly talking about vector math. Yeah. And what does this have to do with physics? Well, we have to know these rules so that we can understand what we're doing. Yeah. What does this have to do with the real world? How am I ever going to use this? Well, we won't. Okay. We also previously talked about vector subtraction. In the case of vector subtraction, of course, we can follow what we've got here up on the board. Draw it out over here as well. Now let me not. So for the case of vector subtraction here, we've got vectors A and B. So our first step when we want to do A minus B, of course it's just to draw vector A. Then we draw vector negative B. So vector negative B is a vector that has the same magnitude, but is pointed in exactly the opposite direction of vector B. Okay. So we draw vector negative B. We place the tail of vector negative B on the tip of A and draw it out. Okay. Then we connect the tail of vector A here to the tip of negative B here, just as they've done in this diagram, and we get the resultant vector that is A minus B. So, let me quickly see what this is. Okay. So in this case, again, we're talking about vector subtraction. And I want to give you an example problem that doesn't have any numbers in it, but just to make sure that we're all on the same page. So, given vector A that looks like this, and vector B that looks like this, and I think we're all done with the slide now. I want to find A minus B. So, what's the first thing I do here? Or what could be the first thing I do? There's a couple of ways. Draw it.
Negative B.
Make negative B. Yeah. So we saw one procedure on the slide there. This one is one for me that makes a little more sense personally. So I'm going to follow that directive right there. First off, I'm going to say that, well, A minus B is just the same thing as vector A plus vector negative B. Okay. So in this case now I need to draw vector negative B. So vector negative B is just the same magnitude as B, but it's pointed in the opposite direction. So something like this. So this is my vector negative B. And my vector B and negative B are supposed to be straight up and down on the board, just so you all know. I may be slightly off in places, but that's my intent. So that's my vector negative B right here. Now I can proceed through with my normal vector addition. I've got A plus negative B. Well, I know what vector A is. I know what vector negative B is, so let me just add them together. I draw A. I put the tail, I need to leave myself a little more space. I draw vector A. I put the tail of vector negative B at the tip of A. So something like this. Okay. And then I just draw a vector connecting the tail of A to the tip of negative B here. So something that looks like that. So this vector that I've got in pink right here is my vector A minus B. So I don't know about y'all, but this right here is very helpful for me to visualize what's actually going on. That formula right there helps me quite a bit. Vector subtraction has always confused me a little bit. It's not intuitive, but that helps. So, again, how are we doing here? Questions? Anything? No? Okay. So, question for you here. I've got vector A and vector B drawn out. And so I want to ask the question, which figure shows 2A minus B? And let me start that. There we go. Cut this off at, say, 45 seconds, I guess. Apparently lost somebody somewhere. So in this case, what we're going to see is that the correct answer is answer A over here. Fantastic. But let me walk through this. So we've got vector A and vector B there, and the question is, well, what's 2A minus B? I've got here vector A and vector B. Well, first off, we recognize that vector 2A just points in the same direction as vector A, and it's twice as long. So multiplication by a scalar just multiplies by that factor, basically. So our vector 2A looks something like this. So this is vector 2A. Okay. Now I said that my vector B is pointed in this direction. My vector negative B will be pointed in the opposite direction. Let me make sure that, okay. My vector negative B will be pointed in the opposite direction. So I just draw my vector negative B in here. Something like that. And then my resultant vector just looks like the vector going from the tail of 2A to the tip of B here. So this is 2A minus B. And that's exactly what we see on the screen here. The setup here is awesome. To fully be able to talk about physical items such as velocity, position, time, so on and so forth, we not only need vectors, but we need coordinate systems as well. Your normal XY coordinate system This is just called Cartesian, C-A-R-T-E-S-I-A-N coordinates. Okay, this can be broken down into 4 different quadrants. So our Cartesian coordinates have 4 different quadrants. And if we draw out our normal picture of x and y, our Cartesian coordinates, we can assign quadrants 1, 2, 3, and 4. When we talk about vectors, it'd be useful to be able to add these in some other ways, just other than just graphical addition. Say algebraic addition instead. Actually makes life a lot easier. And in order to do that, we need to talk about breaking down a vector into components that are pointed in x and y and z directions. So, a vector A can be broken down into component vectors. And our component vectors are parallel to the x and y axis, or axes, something like this. So, for instance, if I have my x and y axes here, and I have some vector A right here, I can break this down into x and y components. I can break it down into a y component that's parallel to my y-axis. So this is component a sub y, and an x component that's parallel to my x-axis. And this is component a sub x. Now, one thing about vectors is when it's useful, we can move them around wherever we want, as long as we don't change their length or their direction. So we've been doing that when we've talked about vector addition and vector subtraction. We've moved vectors around wherever we wanted to. Talking about putting the tail at the tip and so on and so forth. Well, in this case, I'm going to do the same thing with my component a sub x here. So if I draw this out, that again is my component a sub x, and what we see here is that our vector A is just equal to my component vectors, the sum of my component vectors, ax plus ay. And what I've tried to do here is demonstrate that with graphical addition. When I've got vector ax and vector ay, and I add ax here to vector ay, I end up with vector A. So my A vector can be split into x and y components that point parallel to my axis.
So, with the breaking up the vector A of x and vector A of y, would those almost act as like a slope, the rise or run, to make a vector? Which increases this slope, or?
I see where you're going, and we will get to something similar to that.
Okay.
Yeah. Good question. So let's think of some examples from your textbook that the author gives of this idea of vector components. Specifically, we'll look at a few rules first. Okay, so we're going to talk about tactics. Here we're talking about determining the components of a vector. So in this case, talking about determining the components of a vector, it says that when we've got our vector component a sub x, the absolute value here, a sub x, of the x component is the magnitude of that component vector. Kind of difficult to understand exactly what's going on there. We'll look at a few examples. Also, it says the sign of a sub x is positive if a sub x, the vector points in the positive x direction, or negative if the vector a sub x points in the negative x direction. So my sign here of just a scalar quantity a sub x can be either positive or negative. The magnitude of my vector a sub x is, of course, the absolute value of this. And then a sub x is positive in the positive x direction and negative in the negative x direction. And of course the y components can be treated similarly. So let's look at some examples that the author gives. We've got vector A here.